introductions, what the content is going to cover, and then we'll get the webinar started. So thank you for just waiting patiently in the lobby, and then we'll get the webinar started in the next 3 minutes. So we're just waiting for a few more people to join the meeting today. Thank you for attending so far. I'll do the full introductions in a second, and so thank you for waiting patiently while we're just waiting for the other few people to join the webinar today, and we'll be kicking off shortly in the next 2 minutes. So it's now 2 o'clock on the 6th of May. So I would just like to thank you for all joining the second webinar hosted by the National Centre for Additive Manufacturing and MTC Training. This webinar is going to be on design for additive manufacturing. I'd like to introduce myself. My name is Colin Bancroft, and I'm one of the key account managers at the Manufacturing Technology Centre. And what I'd like to do first off is just run through some housekeepings. So all videos and mics will be turned off throughout the presentation. But what we will have is an option for questions to be asked throughout, and I'll be monitoring the chat box function, which could be found as a speech bubble. So you can see the chat box if you just hover towards the bottom of the presentation. And you can just type your questions in there. Just be mindful that everyone can see the questions that are posted, and then what I will do is at the allotted times throughout the actual presentation, give the presenter the option to then answer those questions. If we're running short of time, what we can do is answer any questions via email after the presentation's been completed. I'd now like to introduce the guest speaker for today, who is Miguel Fernandez Vicente, who's an advanced research engineer in design for additive manufacturing, working at the Manufacturing Technology Centre. So now I'd like to please hand over to Miguel, who would like to kindly speak to you about the topic of design for additive manufacturing. Over to you, Miguel.
Thank you, Colin. Good afternoon, everyone. So, as Colin said, I'm part of the design for additive manufacturing team. So, I will presenting today about the how we see design for additive manufacturing. So, and how we can implement that, and what are the challenges that we have on this activity. So to give you a bit of a background where we come from, so the MTC is part of the research network of the high value manufacturing catapult. So that we are 7 centers across the whole UK, and each center is focused on different technologies or have more specialized on different technologies. And in Coventry, the MTC is where is based. We opened in 2011. We are an independent research technology organization. So our main aim is to bridge the valley between the valley of what we call the valley of death between the academia and the implementation on industry. So the MTC is is the base of the National Center for Additive Manufacturing as well. So we have about 100 engineers focused on additive manufacturing projects, not just on additive, um, some of them, but where their main area of working is additive manufacturing. So the MTC is as well the since 2017 is the ESA benchmarking center. So we help ESA embracing some additive manufacturing technologies by identify what are the challenges that we have in there and helping them evaluate those technologies. And since 2018, we are as well part of the AM Sector of Excellence of ASTM. So in the development of standards that will be explaining a little bit more in detail a little bit later of what that means in our design process. So for you to understand how the national center, how we work the different teams. So the national center is not just one team. So we are different teams, each one specialized or with their expertise in each one of the areas. So if you attended last week the materials webinar with my colleague Jason, he is from the materials team where they develop the capability on that side. And we have as well the AM process or the post-processing that you will see that is very important to take that into consideration when we design parts. And as well, we have other teams like the verification of validation or the connectivity and simulation of the components and what will be the manufacturing. So specifically, our design for AM process or our team aims to support the implementation of the software knowledge and as well the exploitation of additive manufacturing. So what our team not doesn't only does design, but as well development of applications. So identifying which applications will be more suitable and identifying if there is some design needed on those. So how do we help industry? What we have is 4 different approaches. So we work with several companies on different aspects of the additive manufacturing journey or the embracement of additive manufacturing. So we have 4 different approaches. So first of all is the awareness, so helping on the awareness of additive, like what is AM, where we can use it. So with identifying those components that could be suitable. Then on the understanding, so understand how we can use additive for specifically our parts. So designing components or identifying which software will be more suitable for that application. Because as you may know, there are many different CAD softwares now developing capability in additive manufacturing. So identifying which ones will be more suitable for that design, that's one of the areas that we work on. As well on the development, so helping additive manufacturing develop. So right now, additive manufacturing is a new technology in some way, even if we are already 30 years in, but there are new developments, new companies getting in. So development of design procedures, so how to implement that, how to go from a conventional method of designing how do we implement that, how we need to, our designers need to change their mind to adapt for this new technology. That's something that we work on, and as well on the development of the marking geometry. So when we want, when there is a new technology, how we design standard geometries that will be useful for us afterwards, and as well on the implementation. So like the development of procedures for using design in additive manufacturing, and as well the trainings that my colleague Colin will be explaining a little in more in detail. So, but the idea of that on the implementation basically is transfer that knowledge into the industry, into you really. So what is our team skill set? So we look at the common design process where we have the concept design and the detail design steps. So we go from the product, what we call product portfolio assessment. So where we go and to company identify which components are more suitable, which ones could be get more benefit, and identify which ones will need a little bit of modification or redesign in order to improve the benefits. And as well the development of concepts, so identifying which tools will need to be applied, like using of generative design or using lattices. That is one of the areas that get enabled by additive manufacturing. And once we have a concept, then we have capability of modeling in many different areas. So we try to be at the forefront of what are what softwares are capable of. So trying to be as much aware as possible of all the tools that are available, and as well helping on other areas where we get as well help from our metrology team, like for example reverse engineering. And as well, we can work on the validation of the geometries once we have the geometry that is ready to go to evaluate and simulate how it will be produced. It will be withstand the forces, and as well if it will be distorted when it's manufactured. And as well on the manufacturing side. So once we have the part and we know that it's gonna be it's all right to be produced. So helping on the build preparation and as well on creation of the drawings. I will go in more detail later. So after presenting what our team goes, and I wanted to talk about the value of why we need design in additive manufacturing. So there are so many technologies. There is so much buzzwords going around additive manufacturing. So why we need design in additive manufacturing? So first of all, we wanted to make a distinction between 3D printing and additive manufacturing. So usually 3D printing is associated with polymer. Doesn't need to be completely into polymer, but usually is associated with the desktop printing. And when we talk about it, you will hear that I will use it several times during the presentation today. And what we mean is basically the process of adding materials. So, but when those parts that we are 3D printing, we are going to use them in a functional way. So for a specific objectives. Then when we talk is about additive manufacturing, because basically doesn't matter if we are adding material or we are subtracting, we are producing a product. So additive manufacturing is not just metal. Usually when you search even on Google, you search additive manufacturing, most of the images that you can find are metal. But really the polymers and ceramic area is a growing areas where we are getting more and more capabilities, and then we can use for functional products. So that's the key difference between 3D printing and additive manufacturing. What we mean on additive is the creation of functional products. So we mean from getting the idea to the final part. So involving as well the post-process of it. So you will see the whole process that we need to cover. And it's not just the printing process. So as I said, it will be the post process. So if we see, for example, the parts that we have on the image on the left, even if they are printing with polymer in a desktop printer, and we are additively manufacturing them, what we will need is to think, okay, which material is the more suitable for for this application, which post-process I will need to use for it. So then what we are really doing is additively manufacture, even if it is with a low quality technology or with a cost-effective technology, then we are using additive manufacturing. So what comprises the design or the design and manufacturing of products? So how the media is selling it is that you basically you want to do that component in there, like the fork end of a motorbike that connects the fork with a brake caliper. You basically, according to the media, you basically have the idea. Okay, I want to 3D print this. Then I could do the design. It's very easy, quick, done, and then print it, and then we get the part. That's it. It's that simple, isn't it? So, do you think is that simple? In reality, we have more challenges that the designer needs to think about when we design for additive manufacturing. So, when designing a functional product, there are some questions that arise. So, like, does it make sense to use additive manufacturing, or which material and technology should be used? So we should be using polymer, we should be using metal, because maybe we can replace metal with polymer. So the technology usually is more expensive than using other methods. So, but I have more geometrical freedom. So where I should put the material. So how can I optimize the material to be put in there? And there are any limitations. So I have more freedom of designing. There are some limitations on it. Or what happens after we print? So that's something, the questions that we have, or when you design a functional product, not just printing of it, but you want to produce a functional product. That's some of the questions that you have in your mind. So I wanted to now open for questions. So what are the questions that you think when you design a functional product using 3D printing, or what are the questions that you think the designer needs to ask himself for using it as a manufacturing technology?
Thank you, Miguel. So yeah, if there's any questions that would like to come in at this point, please feel free to use the chat box. One of the questions that's come in so far previously was, when should I use lattices?
Well, yeah, lattices is one of the geometries that are capable of being produced by 3D printing or additive, and usually you should use them when you want to lightweight some areas, because the good thing of lattices is what we get is getting almost the same performance of the parts, but with less weight. There are some other challenges behind that, but usually are used on those areas.
And then another question that came in previously, that someone's had a few issues when printing parts. So how can they determine if the part was going to break?
Well, I will explain a little bit later about this specific challenge that we have in there. But basically, what we need is to follow a process for evaluate what will be the properties of the parts before we go to produce the final part, and validate our process for the final component.
Excellent, thank you, Miguel. I don't see any further questions that have come in at present, but please feel free, if there's anything that you think or would like to ask throughout the presentation, don't hesitate to put those in the chat box, and then we're going to present those to Miguel throughout. So I'll let you carry on then, Miguel.
Okay, thank you. So the reality when we design products, so that's what. Thank you, Colin, for the question. So you will see that now. What is the reality when we design a functional product? So we see that steps that how the media is selling it, well, how we design for additive manufacturing. We can see that there are many other steps that need to be taken into consideration when we design for additive manufacturing, where we have different challenges. So I will go one by one of these workflow for design. So when we have an idea, so starting from the left, First of all, we need to identify what are the requirements of that application. So as an example, I put before the motorbike fork, the fork end, is capturing what are the requirements that our part needs to be. And it is something that is already been used in for other processes, or the requirements capture for the design engineering. But in additive manufacturing is a key step, because we have so much geometrical freedom within additive manufacturing, that it's very important to understand what is important in our component. What are the requirements that we have in there? Because as well, we have different materials. Some of the situations where maybe a part is being produced right now with metals, but if we capture the requirements properly, we can identify that a part could be produced by polymer, for example, or 3D print using additive manufacturing of polymers instead of using metals. And then we are saving thousands of pounds or dollars on this step. So then it's very important to have these requirements captured. And then once we have those requirements, what we define is what we call systems design, where we basically put those requirements into a structure of where are our loads, what are the important areas on the geometry, without knowing what is going to be inside of those limitations. So in the case of the brake caliper, the connection in the case of the fork end, the connections with the brake caliper, for example, that those are areas that are going to keep anyway. Doesn't matter how it's going to be our geometry, we will be using the same connection. So then we need to keep them without knowing what is going to happen in there. But then we can add loads. And then from there, what we can do is creating our concept. So in our day-to-day design activity, we use as well software or computers to tell us what are the ideal areas where to put material. So like, for example, using topology optimization or generative design, what those softwares do basically is giving you a concept of what will be your geometry, where you should put material. And then what we'll need is to use our engineering knowledge or design knowledge to reinterpret. So going from the concept to the remodeling, reinterpret those results, and then create our part. And this remodeling step is very important, because we are going from what will be a concept, something we say not defined or not physically fitting within the requirements or with the technology. And what we do in the remodeling step is modifying our geometry to fit within the requirements, and as well with the build and what is going to happen after the build. So I will be explaining a little bit later about that. So in this step is where we modify our geometry, and is where we create what will be as an end part. So what will be our expected end part at the end. So once we have that, then what we need is to validate our design. And this is where we can check, regarding the question that was asked before, is where we can validate our design and make sure that it's not going to break. So at least in the simulation inside of the computer. And that's when we know that the design is right. Then what we do is modifying our geometry to adapt it to the specific process. So adding some areas, adding material where it's needed, in order to fit with what are the restrictions of the process. So, for example, adding material in areas where we are gonna be removing, for example, for sanding, or we are going to machine surfaces. So then what we need is to add those materials and modifying and prepare the part for that, for the building. And then after that, what we do is what is called build preparation, which is a step where we add support or orient our part according to the buildability, and as well stack more than one component. So then what we get out of this step is the file ready to go to the machine. But one thing we do before going to the machine is check that our process is going to be is not going to fail. So some of the technologies, there are some distortion that happens inside of the build, or that could happen. So then what we do is basically simulate what will be the process inside of the computer. And then if there is some distortions, then counteract those distortions for printing a distorted part that when it during the process, it will deform, so then it will be all right at the end. And then while we have that, almost all the additive manufacturing processes work layer by layer. So basically what we need is to, from our CAD file of the whole volume, separate the part in layers and and create the toolpaths that the laser or the head or the liquid it will be following to create our geometry. So then it's an step where we are creating the instructions for the machine to build. So then we go to the build, and as you can see, there is some gap between what happens between the build and in the end part, and that's a key point or key element of difference between 3D printing and additive manufacturing, which is what is happening. And the designers, I said that before in the remodeling, and that there is something happening after the build, and you can see that even now from the remodeling step, the green one, and the build, there are 5 stages that the media it doesn't contemplate, and are key points where there are challenges in there, and there is a lot of knowledge to be applied on there. But after the build, there is almost all the technologies need some post-processing afterwards. So some of the technology we need to add supports or heat sinks on the parts to be printed properly. So then we need to remove those supports, or we need to finish some areas or machine some areas. So taking that into consideration, even on the remodeling step, is very important, because there will be some areas where we will be removing material. So then if we don't take that into consideration, then we won't be able to remove that material. Or if we create areas with supports where we cannot access them, then we won't be able to remove those supports. So this is important to know what is going to happen afterwards, or what is going to be the plan of post-processing afterwards in order to implement that. And okay, we do the post-processing, we remove the supports, we do all of that, but then I get the final part. In reality, what we need is, when we do a functional product, we need to know if what we get out of the manufacturing is the right output. So then what we need is to inspect our parts, measure them, or even in some cases, in some of the technology, in the criticality, depending on the criticality of the components, what we will need is to scan the parts and look inside of the components to see if the part is properly produced. And as you can see, there is these steps. We go from the idea to the end part. There are many steps that need to happen during this process. But when a designer needs to design parts for additive manufacturing, there are as well 2 steps that happen even before that. So which are identifying which components and the materials. I will talk a little bit later. But you can see that the designer has basically 2 mindsets within, or we have 2 mindsets where in the design process. One is the design for opportunity, so trying to optimize, get the most of the technology as possible. And then what we do is starting thinking or modifying our mindset to mitigate the risk. So what could be the failures that could happen, or what would be where we can fail and not get the right output out of it. So then we do the risk mitigation. So the 2 steps that I said before is that before identifying which components are feasible, if it will be benefit from additive manufacturing, which is a key element. So how we can get the benefit out of it, and that's a key element, because of the how it won't make sense to produce some parts that could be produced by other processes in a cheaper way, or produce components that are very expensive to be produced by additive, or very challenging. And as well, once we say, okay, this part will be suitable, but which process will be more suitable? Because maybe, as I said before, maybe we can identify some parts that are produced by metal, and could be produced by polymer technologies or by ceramics. So then identifying which process will be more suitable. So then that's why during this whole process, as you saw, there are many steps. That's where we need as well the support from people from different areas where they have expertise and they are aware of the latest capabilities of the technology. For example, in our team, we work with the AM process team where we have experts on ceramics, experts on polymers, or experts in specific metals, and they are aware of the latest development in industry. And that's one of the key things we have on the National Center, where what our aim is to support the industry, giving expertise in different areas and try to be at the forefront on what is happening. So if you look at what will be the confusion with design for additive manufacturing, many people confuses this with, okay, this is just a design for manufacture, like any other technology. It's something that we have implemented. Well, if you can see, really the design for manufacture happens only on that step. So all the other steps is something that is away from what is the design for manufacturing activity, or the typical design for manufacturing activity. So what we want to refer to is that really what we do, or what the designer for additive needs to be doing, is design with additive manufacturing, with the capabilities that we have in additive manufacturing, and with what can be done. So really, basically, there are 4 objectives to be done. So the designer with additive designs the right products with a suitable process, with an optimum design, so optimizing for what are those requirements, and with a correct output. So basically covering that design for opportunity, but as well mitigate the risk, so then getting a correct output. So I wanted to show the 2 very quick examples. So the first one is why we need a design for additive. I want to show an example from GKN, where we can see some manifold. So manifolds are engineering components used for controlling the fluids in many different applications. So usually are produced by machining blocks. So then when they applied design for additive manufacturing for these components, you can see that there is the big difference between a weight of 30 kilograms to 5.5 kilograms. And we say, okay, yeah, that makes sense, because those guys are doing aerospace components. In aerospace, it's important to have lightweight, because then you spend more money on flying planes. But when we in reality think about it, is that the parts in additive manufacturing, even if we see on the right the image and we see a block of metal, in reality, all the technologies in additive, or almost all of them, use a discrete head, or a single head, or a laser, or something like that, or an electron beam to create the components. That means that we have very thin laser, or very thin head, creating each one of the layers, and many layers for creating a component. So for example, in that one, if we make a very rough estimation of how much it will be, so assuming that the component is 150 by 50, I don't know exactly the dimensions of that component, and we think about 0.1 millimeter layers, that is a very common layer thickness, and with a beam diameter of the laser of 0.7 millimeters, that means that the laser, to create that component, needs to travel 3,500 kilometers to create that. So you can imagine the amount of hours, even if the laser goes very fast, the amount of hours that requires just to move the laser on top of the part and then melting the powder that will be create that component. And everything with other technologies, it will be even slower. So just doing that, a rough estimation of what will be for the other component with the weight, we can see that the difference is that we are traveling just 700 kilometers. So there is a massive reduction on the traveling, and of course this will change on the cost. And you can say, okay, yeah, it's gonna take more time, less time. It doesn't matter, because in reality I will spend more time, I don't know, finishing the component rather than building. But it's not just that. So in the case of the hydraulic manifolds, the way they are produced right now, in those areas, what we have are efficient loss, dirt reservoirs that cause failures, and as well we can have leakages between adjacent channels. So we have some issues already on the current manufacturing of manifolds in those kind of things. So what we can do with additive manufacturing, as we have more freedom, what we can do is optimize the flow of the channels, not just saving material, but using the geometrical freedom to improve the functionality of the component. So then we can create smooth channels. Then we reduce the risk of leakage of the bores, and as well we have more design flexibility. So we can even tailor each one of the manifold to each customer, and it won't be a massive change in the process. So then we have more benefits of having them there. So that's one very simple example of what is the value. But one of the things we work as well in our team is looking on what is coming as well, what are the features of the technologies that can be done. So here we have an example where we use inspiration from a ATA project that you can see on the left, where this is an engine air brake for jet engines. So what we did using that inspiration is create an assembly that is built inside of the machine. So you can see the image in the middle. Basically, the blades and the structure are printed together, but they are separated. So basically, the only step from the image on the middle and the image on the right that is moving, we remove we cut the part from the build plate and add some gears on the back to allow the movement or to animate the structure. And that's something that right now is a little bit early days on implementation of moving assemblies printed directly inside of AM parts, at least in metals. In polymers, there is a little more development on that side. But that's only one of the areas where, as I said, there are benefits, or we can get many benefits out of it. And when there is the value of design is where it gets produced, because usually you will say, okay, I want to 3D print the blades, and then we will go print the blades using additive, and that's on. But that's where the design can look at the whole assembly and say, okay, I think it makes sense not just to print a blade, but let's look at the whole sub-assembly, because maybe what we can do is consolidate different components and then create a more clever, and then we will get is more optimal and get more benefits. So these two benefits that I saw before, there are just two of the whole all the range that we can do. So there are many areas where we can design for them, can add value and add benefits on additive manufacturing in the current processes. So we can embed components, for example, we can create metamaterial structures, or implement shock absorption structures. So having that freedom, we can add that. And as I said, we have many areas where the designer, when we have that first mindset of design for the opportunity, is where we need to use some of those benefits, look at them and say which ones we can use in there. And this is not a fix, so this is just a gathering of some examples or some benefits that we gather for this webinar. But this is growing. This is something that the one thing we have on additive manufacturing is that keeps growing. More people is getting involved. So then one of the things we do in our team is keeping track of what is happening, what are the latest, and what are the most beneficial things that we can implement on additive. It's very exciting area to be involved in because of those reasons. But what I said before, that we have those two mindsets. So in terms of the risk mitigation, is that okay? What could happen? I mean, those are expensive machines. What could go wrong is if you have used a 3D printer at home, or if you have seen some failures on printing. There are so many different areas that a machine could failure. But even if we think about the most high-end technologies, so we have here an example from GE where I think it was an application they were working with Airbus on this bracket, creating this final component that usually the media just shows that like, okay, and the first 3D printed bracket or the first 3D printing tree or whatever. In reality, to get to that step, most everyone that has an additive manufacturing machine has what we call the bin of the broken dreams. So where to get to that point, there are many parts that get failed on the way. And one of the things we do within the design for additive practice is specifically try to reduce the size of this bin. So try to reduce that area and using the knowledge in order to improve on the journey to reduce the failures and the risks of failure that could happen on this technology. And if you have used a desktop printer at home, I'm sure you had already some failures on specifically because of the design, because you didn't design it properly, and then if the machine failed. So then what's where we are trying to support on there. So how do we integrate all that knowledge or all that workflow that I've been talking about? So as I said, the design with additive manufacturing, the designer needs to approach those right products to produce the suitable process and the optimum design and the correct output. Basically, what we have is 3 different hats. So where we need to be a design engineer, and sometimes we need to be a manufacturing engineer because we need to implement all the manufacturing requirements or even the post-processing. So we need to be aware of what is happening, what are the post-process, what are the requirements from there, and then that's why we need the help from special or for experts on each one of the technologies. And as well, sometimes even for identifying the right products or the suitable process, we need at the hat of the cost analyst, where we need to evaluate what are the costs involved from there and where are the most beneficial components. So if we need to compare 2 components and say, this makes sense to print this one instead of the other one, we need those costs to evaluate them. So how do we transfer that knowledge? So what are our approach of having there? So as the process of design is non-linear, so I put that in a workflow that seems linear, when in reality we're jumping from one step to another. We iterate many times on these steps. How we are trying to, in terms of transferring that knowledge, is creating learning modules with hands-on activity just after that, and then after having 2 or 3 learning modules with hands-on, then doing an evaluation, and then after that moving to the next step. So that helps us is to grow in implementing that knowledge, and then because at the end, once we are in the design workflow, as I said, in the remodeling step, we need to you need to already think how I'm going to inspect the part. So then and implement that even on the very early on the process. So to transfer that knowledge, that's why we need different iterative process on having that. So what are the design considerations, or what we say the modules that we've been developing that we think are key in terms of using design for additive? So first of all is understand the workflow. So as I said, I presented today what are the workflow and how we can implement that. When we use additive manufacturing, that's a key element as well. Or how we change our design, our thinking when we're using additive manufacturing. As I said, the example of GKN, how we can implement, how our designers needs to modify that approach. So then that we need to implement as a design consideration, as well as selecting which component will be more suitable, or the cost of additive manufacturing. So how we can implement those costs, identifying those costs. That's something of the modules that we try to transfer in our knowledge transferring activities. And the generative design in general. So as I said before, between the steps of system design, of the the third step and the concept generation, how do we use those software tools, or so which tools we use for having this? So that's a challenging step where there are growing software tools capable of doing new implementations. So how would we integrate them? And one of those areas specifically on generative design is the design of lattices or cellular materials. So how do we use them? Which type of lattices we should be using? So that, I think there was a question before about that. And as you can see here, I changed the color of the box, and related to what the arrows of before on the design for opportunity and the risk mitigation. So where we have a different mindset. So we have all those green ones that said before, where we are trying to optimize and get the benefit of additive manufacturing, and the design for manufacture is a key step on the design process. And how do we, what are the geometrical features that we should be taking into consideration for having this? So there are some specific ones. And as well, how we design for materials in additive manufacturing, because materials are different. So we have different types of material, but as well the behavior of those materials is different. So how do we look at them? And that's one a key element that to understand when we design for additive. And as well, how we design for the post-processing that I explained before, and the inspection. So we know, so our metrology and post-processing teams, they know about the technology itself, but what we need is to transfer that knowledge into the designer, how we implement that knowledge into our design, and what are the key elements that we need to take into consideration when we do that. And another module or another design consideration on the design for opportunities, how we select materials and processes. So when we identify a component, how we do that selecting of materials and the processes that will be more suitable for that application specifically. And one step is the build preparation. So that will be those two steps of build, model preparation, and build preparation in the middle of the workflow on the top, where the identification of or the approach of how we prepare the builds, how you approach that, and how you get the right output of the manufacturing. That's a key element to be understanding here. And as well, the process simulation. So as I said, in some of the technologies, specifically on the metals, the metal side of things, the metal area, that's a key element, as we could have failures due to specifically to the distortion of the components. And as you saw that there are many steps, you can imagine the amount of data that is generated during all those steps, and the people that you need to talk with in the different steps. So for example, we need to know, it is important to know how you talk with the manufacturer, with the CNC team or the machining team, to let them know which are the areas that you need to machine, and what are the tolerances that you are expecting from it. So there are some other documentation that needs to be implemented in order to be able to track what is happening across the whole workflow. And one of the other things to understand as well is that this technology, even if it is young, one of the key things is that we as it's growing so fast, and that we are seeing more distributed manufacturing across the world, and there are different manufacturers of the machines. We need standards in order to be able to talk the same language. That is the main purpose of the standards in general. So trying to help talking in the same language, that in a way that if I design a part here and I try to print or want to print or manufacture in a different country, we can adhere to the same standard, or make sure that their output is going to be the same that if I'm going to produce it here. And as well, as I said, one of the things we think is an important to think when designing for additive is that what are the challenges that are ahead, what are the challenges that we have right now, and what is coming, because these technologies are evolving so fast that it's important to know what is coming, because maybe something that you cannot do it today, in 2 months' time, a manufacturer is going to be able to produce those components, or there is a machine manufacturer that have developed a new technology where you can implement that, or they are already almost there. So then we can produce that, and we can get those capabilities. So this, as I said, these are the key steps or design considerations to be summarizing that workflow on the top. So as those boxes on the bottom are what I wanted to transfer in there. And with this, I will open for questions that you might have on the whole presentation. And thank you.
Thank you, Miguel. Yeah, we've got quite a few interesting questions that have come in over the course of the webinar to date. So one of the questions is, how do you consider durability requirements of a part in additive design where there are so many uncertainties with material and processes, especially with laser powder bed fusion processes with metals?
So what? So yeah, it's a challenge, and what we will need is to design a qualification program to develop the design allowables in order to validate the process. So basically, how the is being implemented right now is fixing steps on the process. So once you have developed, I would say the first developed part, what you start is fixing some fixing next steps on the whole manufacturing process. So then what you get is repetition of the same with the same conditions. So even fixing the same machine. So validating one machine, and then that machine is validated, but then the one next to it is not validated till you make sure that it's producing the same parts. So that's how it is being approached specifically on the powder bed fusion technologies.
Oh, that's great, thank you. And then I suppose that leads into the next question. So during the validation, can we use topology optimization to make sure that the part is safe? And also, we're not adding extra material onto the functional area. And then will this cycle remain the same if we're using jetting technology for producing metal parts from digital metals, desktop metals, HP metals, or exome?
Okay, I will go one by one. So in terms of the validation step, where we use topology optimization is in the concept generation. So where we basically optimizing where we put material, so then we get a concept of our geometry. So then we can use then FEA software tools. Some of them have implemented as well both capabilities. But in reality, what we get out of the topology optimization usually is not the final part that we're going to produce directly, because we need to add some areas where we have fixed connections. For example, in this case, we have the very caliper connections, and those needs to be exactly the same as they were before. So then what we need is to use a different tool, or even on the same software, you can they have a module for topology optimization or generative design, and another module for validation, where you can get that validation of it. And can you repeat the second?
Yeah. So the next part, the second part was, will this cycle remain the same if we was using jetting technology for producing metal parts? So technology from digital metals, desktop metals, HP metals, and exome.
Well, this workflow, there will be some other steps. So, for example, when in the jetting materials like desktop metal or those kind of things, after the build, what happens is that there are other post-processing happening afterwards, where the part gets modified. So, for example, removing the binder in the part, and we need to think about it as well on the remodeling steps. So really, I put the example that we can see here is powder bed fusion, but in terms of the overall steps will be very similar. So there will be in terms of the process simulation, there are some the tools are still developing, so there are some technologies that are more developed than other steps. But we can think that in the post processing, depending on which technology you are using, it will be completely different. So thinking on technologies that are very different, for example, in the slicing, it will be in extrusion base, or in desktop printing, you prepare the toolpaths of your head, while in powder bed, what you prepare is the hatching on each layer with your laser. In some ways similar, but there are many different things that need to be implemented in the remodeling step.
Thank you. We've just got time for a few more questions before we go on. So another question that's come in. So is there software for simulating and validating the potential strength of an AM design? And in the planning phase, can you assess the cost benefits or penalties versus conventional manufacturing?
Can you repeat that, please?
Yeah, so is there software for simulating or validating the potential strength of an AM design? And then there's a second part. In the planning phase, can you assess the cost benefits or penalties versus conventional manufacturing?
Yeah, so there are softwares that are capable of implementing those validation. But one of the key elements is to make sure that what you are simulating is what is happening on the manufacturing. So usually what you need is to do the process simulation, and then using that process simulation values to implement them in the validation process, so in the validation step. So as I said, I put it in a linear process, but you need to jump. Sometimes we need to reiterate into these steps, and in order to get a functional product.
Thanks. Probably got time for one more. I know there's more questions that have come in during the webinar itself, and what we'll do is we'll look to respond to those via emails afterwards. But one of the last questions is, what key software would you recommend across all phases in the design for additive manufacturing process?
That's challenging, to be fair, right now. So there are some, we say the major CAD software companies are all of them right now. We are lucky because of it, because like 3 years ago there was not something like that. All of the major CAD software companies are working on implement these workflows inside of them, because they are, bear in mind that some of the tools are very specialized on a specific area. So as I said before, there are some tools specifically for the process simulation that are from some of the software vendors, but there are other tools specialized on the concept generation. So whether there is an implementation of some of the softwares are implementing as much as possible, but it's always challenging to get to pick one, I would say. So we have, so for naming some of the software companies, I would say from PTC Creo, they are implementing the whole workflow as much as possible. We've seen as well Siemens NX is implementing the whole steps as well. Dassault, they are implementing in their CATIA or online, not online, their software catalog as well, so implementing all the workflows. From Autodesk, we have as well Fusion 360 seeing that is implementing most of the technologies, although they have some of the tools are separate softwares that can be implemented, or you need to go to a different software and then go back. So as I said, is right now is not at it's not that you can use a tool for almost everything else, but the software companies are on board, and almost all of them are trying to get into it. So like, for example, ANSYS is implementing as well, or Hexagon is doing they are implementing as well different tools together in order to simulate the process, be able to do FEA, and then doing the CAD as well. And ANSYS is doing the same thing, so having CAD software as well as validation. Of course, ANSYS is their main areas on the validation and simulation, and as well implementing other tools. So we are seeing more implementation of those kind of things, and the machine manufacturers are as well very actively working with the software companies, because at the end that's an issue we have, all of us. So that one of the challenges that we have in there is jumping from software to software, is that you have the risk of losing the design intent. So if I design a surface that needs to be with this tolerance, and if I keep moving from software to software, exporting in a different file format, what I get at the end maybe it's not going to be the same, or there are different versions. So then I have the challenge that the version that is going to the machine is not the latest one that I want to print. So yeah, it's one of the areas or the challenging areas that we are actively looking after and try to help software companies as well, providing feedback and with the manufacturer and working with as many people as possible.
Thank you so much for that, Miguel. Just mindful, we've got 3 minutes left of the webinar time frame, Miguel. So if you wanted to carry on with the presentation at this point, and then we can pick up any questions afterwards.
Yeah. So.
Yeah. So
to you.
Yeah. So this is I work for the Advanced Manufacturing Training Center, which is aligned to the Manufacturing Technology Center itself. And what we've got is we've got a number of training solutions that can actually support with the adoption of additive manufacturing, looking at the requirements capabilities right the way through to the full design for additive manufacturing process. What I've done is I've provided some links on there for you to look at for additional information. So a link to the actual training website, but also a link to our training needs analysis tool. What this does is you can actually look at specific criteria within the training needs analysis of what it is that you're trying to achieve. What it will do then is ask you a number of questions, either you individually or it can be allocated to your team, to look at what specific skills requirements or skills gaps that you may have and what needs to be addressed to support you with the adoption of these new emerging technologies. So what I would do is that I would recommend anybody that's looking to get into additive to first undertake the free training needs analysis. And then what that would do then is help you identify which training solutions are most appropriate for you and your organization in adopting this technology. What we'll do is make sure any questions that haven't been answered throughout the webinar today will be passed over to Miguel. We'll get those answered and then emailed out to you. The session has also been recorded today, so the recording will also be made available and the link will be sent out to that recording for future review. And I hope you've really enjoyed today's webinar, and we'd really like to thank Miguel for his expertise in putting all of this together. And thank you very much for attending, and hope to see you next week at our Advanced Introduction to Additive Manufacturing webinar at the same time. Thank you very much.
Thank you all.
Thank you.